Hello everyone, welcome to my channel Dr. TAPATI'S presentation. Myself Dr. Tapati Vanjade.
Today in this video, topic of the discussion is determination of 𝛼-Amylase activity using Standard Curve of Maltose.
Alpha-amylases are universally distributed throughout the animal, usually pancreatic and salivary. In plants, especially barley, millet, wheat, sorghum and maize, and in the microbial kingdom, we can find various bacterial and fungal sources for the alpha-amylase. Alpha-amylases are either extracellular or intracellular. Let's do the estimation of alpha-amylase activity. In alpha-amylase assay, starch is the substrate and maltose is product. Therefore, we have to take starch solution and we have to add alpha-amylase in starch solution, and after few minutes of incubation at optimum pH and optimum temperature of the enzyme, we have to measure maltose content in the reaction mixture, and then we will calculate maltose conversion per unit unit of alpha amylase by measuring the micromole conversion of maltose per ml per minute. Let's know the method of alpha amylase assay. Alpha amylase activity is estimated by following the modified method of Okolo et al. 1995. In this case, 1% starch solution is prepared by heating appropriate amount of starch in 0.1 molar acetate buffer at optimum pH of alpha amylase. In the test sample, 0.5 ml acetate buffer and 0.25 ml properly diluted enzyme were added with 1.25 ml of 1% starch. So in the test tube, 1.25 ml of 1% starch plus 0.5 ml of acetate buffer and 0.25 ml properly diluted enzyme are added, and the mixture is incubated at 50 degrees Celsius or optimum temperature of alpha amylase for exactly 10 minutes. For the enzyme blank preparation, 1.75 ml buffer and 0.25 ml enzyme are mixed very well. In this tube, we are not adding starch solution, only buffer and enzyme. So in order to minus the sugar content in the enzyme, we are taking this value, value of absorbance for sugar content present in the enzyme sample. Now for substrate blank, 0.75 ml buffer and 1.25 ml of 1% starch are mixed in separate test tube and incubated for 10 minutes. So in the substrate blank, we are taking buffer and only starch in order to get the value of reducing sugar content in 1% starch solution. Now after the assay, after 10 minutes of incubation, 0.2 ml of reaction mixture from all the test tubes, this one and enzyme blank and substrate blank, from all the test tubes is taken and added to DNS solution containing 3 ml DNS and 0.8 ml water, because in the standard curve, in order to get the standard curve of maltose, we prepared 3 ml DNS and 1 ml of maltose solution, and then we heated that. Therefore, in this case also we are making total reaction mixture 4 ml, where 3 ml DNS and 1 ml sugar. So we have to measure sugar content of 1 ml of reaction mixture. Now the tubes are kept in boiling water bath for 15 minutes. Then 1 ml of 40% raw jelly salt solution is added and cooled. So it is the Miller method. Absorbance is read spectrophotometrically at 575 nanometer according to Miller 1959. So these last steps are for the DNS method in order to get the reduced sugar content in the reaction mixture. Here we are measuring maltose content. In order to get actual maltose released by the action of amylase, we have to subtract the absorbance of substrate blank. This is the substrate blank. So we are subtracting substrate blank value and enzyme blank value from the test sample. This is the test sample. In this way, the subtracting optical density or absorbance value is the actual absorbance value for by the action of 𝛼-Amylase.
In the unit 19 and 20, already I have discussed about DNS method or Miller method in order to make standard curve of maltose. Links are provided in the description box. You can check that.
In this experiment, you will get maximum absorbance value in test sample, where we are taking enzyme and substrate mixture, and after the incubation, product formation will be there. So intensity of the color is higher as compared to substrate blank and enzyme blank. In substrate blank, only substrate starch is present. So we are taking this value because few amounts of maltose may be present in the substrate in the soluble substrate soluble starch solution. In case of extracellular microbial 𝛼-Amylase, you may get sugar content in the crude extract. So we are taking this enzyme blank value where only enzyme sample is present. We have to measure the maltose content in the enzyme sample. In that case, we will find the actual absorbance for the calculation of 𝛼-Amylase activity by subtracting absorbance of test sample minus absorbance of substrate blank plus absorbance of enzyme blank. So this value is required for the calculation of 𝛼-Amylase activity. Now we have to use this standard curve of maltose for the calculation of 𝛼-Amylase activity. In this standard curve, we have plotted in the x-axis concentration of maltose in micromole per ml, and in the y-axis absorbance at 575 nanometer. And we found this equation y is equal to 0.581x, and from this equation we can measure x value if we know y value, where x is equal to 1 by 0.5851 and y is equal to actual absorbance value. So if you know the y value or actual absorbance value, we can measure concentration of maltose in micromole per ml. If y value is 0.523, then x will be 1 by 0.581 into 0.523. We are putting y value or actual OD as 0.523, then we will get x value as 0.894. So this point will be here, almost here, 894. X value is 894 here almost, and y value is 0.5 here. If it is the 0.5 value, then we are getting here as the 0.94, this point. Now this 0.894 micromole maltose is for 0.2 ml reaction mixture, but we have to calculate it for total 2 ml reaction mixture. Therefore, we have to multiply the value with 10, because total reaction mixture is 2 ml, that is 2 divided by 0.2, that is equal to 10. Now see the method carefully. We took 0.2 ml reaction mixture in order to estimate the reducing sugar, but in the experimental in the test sample, total reaction mixture of substrate and enzyme is 2 ml. 0.5 ml plus 0.25 ml plus 1.25 ml, that is equal to 2 ml. So total reaction mixture is 2 ml, but from 2 ml reaction mixture we are taking only 0.2 ml reaction mixture in order to estimate the reducing sugar content, because if we take total 2 ml of reaction mixture, we will get very high OD, that will be that may give you the error result. Therefore, we are taking very small amount of reaction mixture, that is 0.2 ml, but we have to calculate for total 2 ml of reaction mixture how much amount of maltose content is present, and we have to measure. We took 0.2 ml enzyme, 0.2 ml properly diluted enzyme we took for the reaction, but we have to calculate for the 1 ml. Hence total maltose released by 0.25 ml enzyme in 2 ml total reaction mixture is equal to 0.894. This is 0.894 for 2 ml reaction mixture, and we are multiplying it with 10, that is equal to 8.94 micromole maltose present in the 2 ml reaction mixture, and in 2 ml reaction mixture 0.2 ml enzyme is present. Now 1 unit of amylase activity is defined as the amount of enzyme that liberates 1 micromole of reducing sugar, in this case it is maltose, per minute per minute under the assay condition. So activity of the enzyme in unit per ml is equal to total maltose released in total 2 ml reaction mixture in micromole content divided by volume of enzyme taken in the reaction mixture in ml into reaction time, that is in minute, because we have to calculate it per minute. If we put those values, then we will get 8.94 micromole for the total maltose released in total 2 ml reaction mixture divided by 0.25 ml, that is for volume of enzyme taken in the reaction mixture, and we are then dividing with the 10 minutes because the incubation period was 10 minutes. If you calculate it properly, we will get 3.576 micromole per ml per minute, that is equal to almost around 3.6 U per ml. Micromole per ml means the unit, so actual value is almost around 3.6 unit per ml. If you are doing dilution of the enzyme before the reaction, then you have to multiply with dilution factor. In that case, activity of the enzyme in unit per ml will be total maltose released in total 2 ml reaction mixture in micromole into dilution factor divided by volume of enzyme taken in the reaction mixture, that is in the ml, into reaction time in minute. In this case, in my experiment, dilution factor is 1, therefore unit per ml will be 3.6 into 3.6 unit per ml. If your dilution factor is 5, then you have to multiply with 3.6 into 5. If you don't want to calculate enzyme activity following the stepwise method, you can directly measure it following this equation: OD into slope inverse into 10 into D divided by V into T. Here OD is equal to actual optical density, and slope inverse S power of -1 is equal to slope inverse obtained from the standard curve of known concentration of maltose. Here we got slope inverse is 1.71 because from this equation you can see that m value or slope is 0.5851. So slope inverse is 1 by 0.5851, that is equal to 1.71. Now D is equal to number of times the enzyme is diluted or dilution factor. V is equal to volume of enzyme taken. Here this V value is 0.25 ml, and T is equal to time of equation. In this case we are incubating the reaction mixer for 10 minutes. So if OD actual optical density is 0.523, and from this graph we are getting slope inverse 1.71, and as I told you, initially we are taking 0.2 ml of reaction mixture in order to get the reducing sugar content through DNS method, but we have to calculate reducing sugar or maltose content in 2 ml, so we are multiplying this 10. and we are multiplying dilution factor as 1 because here we are not diluting the enzyme. And 0.25 ml is the volume of the enzyme taken for the reaction, and 10 minute is the incubation time. And again we are getting the same amount of enzyme activity, that is around 3.6 unit per ml. So this is the actual formula for enzyme activity calculation. In order to get calculate this, we need slope inverse value, and the slope inverse value we will get only from the standard curve of Maltose. Whenever you are preparing DNS reagent, you should every time you should make a standard curve for Maltose, and then only you should use that DNS reagent for the calculation of enzyme activity. In this case, I have taken arbitrary values for absorbance and arbitrary values for concentration of maltose in micromole per ml, in order to make you understand that how to calculate enzyme activity directly from standard curve. You may get separate data. I hope you understood the topic very well. Thank you very much for watching this video.